Now let's move on to probably the most complicated data structure we've covered so far, which is binary trees. We're actually going to be using pretty much every topic we covered so far to understand binary trees because there's a lot of complexity to them. To start with, we're just going to understand the structure of binary trees. They're similar to linked lists in that we have nodes which have some kind of value. I mean, it could be a character, it could be an integer, or it could be a string, it could be an object. There could be anything contained in the value of this node. To keep it simple, let's assume we have integers, and let's say we have the integer 2 here. And we know that these nodes are no fun unless we have some pointers to connect them together. With binary trees, as the name implies, binary, which means 2, these nodes are going to have 2 pointers. But with linked lists, we had some next pointers and previous pointers for doubly linked lists, so it's kind of similar to that in a sense. It's similar to a doubly linked list node, but in this case, we draw the pointers typically down, and that's because there are some relationships with these nodes. We call this the left pointer and the right pointer. And when we have a pointer like this that's connecting it to another node, let's say a 1 value here, that node is also going to, of course, have a left and right pointer. Now, these nodes have a relationship. It's not like a linked list where nodes are just connected left and right. We say the relationship between these nodes is that this node is the left child of this node. So there's a relationship called the child relationship. This is a child of the parent node. So this node is considered the parent node of this node. But as I said, since this is the left child, this node could also have a right child. Let's say the value is 3. This node is also a child of this node, and this node also has the same parent as this node. Both of these nodes have the same parent node. And what about these 2 nodes now? Well, this node does not have a left child as of now, and it does not have a right child either. We can assume that these pointers are pointing to some default value of null. They're not actually pointing at any real nodes. And when we have nodes like these that don't have any children, we call these leaf nodes. So this would be a leaf node, and this would also be a leaf node. But what if for this node we actually did have a child over here? Let's say it's 4. Then this node would no longer be a leaf node. This node would be a leaf node. It doesn't have any children, but its parent node over here does have a left child, so it's not a leaf node. With binary trees, we're always guaranteed to have leaf nodes. If we start at the top of the binary tree, which by the way is called the root of the binary tree, the top node is always called the root node, whereas the bottom nodes are called leaf nodes. And these are, terms that come from trees in general. Trees have roots. Trees also have leaves. But the interesting thing here is you might have noticed the root goes at the top and the leaves go at the bottom, which is kind of the opposite of a regular tree where, let's say you had a tree that looks something like this, where the roots would be at the bottom of the tree and the leaves would be at the top of the tree, but we know that that's not the case here. So that's just an interesting point about trees. We kind of draw them upside down, but these are important terms that are used with binary trees. Of course, every tree is only going to have a single root node, but it could have multiple leaf nodes, and it's guaranteed to have some leaf nodes. But why is that the case? I mean, what if I had from every single leaf node, one of the pointers just pointed back up to the root? I mean, we had that with linked lists, right? In some linked lists I talked about, you could have a cycle. But when it comes to binary trees, we are not allowed to have cycles. That's part of the definition of a binary tree. We're not allowed to have cycles. So since binary trees can't have cycles, that's the same reason why 2 adjacent nodes like these can't be connected. We can't take the right pointer of this and then connect it to that. That would sort of form a cycle. Now, technically this here does not form a cycle because each of these pointers connecting nodes can only be one way. We can only go along it in one direction. But the definition of a binary tree, we say that it doesn't form any cycles, basically assuming that these pointers are not directed. Right? Assuming we could go both ways, there should not be any cycle in the graph. So therefore, we can't connect these 2 nodes together. By the way, nodes like these that have the same parent are considered sibling nodes because they share the same parent. So, that's where this word comes from, sibling, like brother or sister. And I guess it's hardly worth mentioning, but all the nodes in a binary tree have to be connected together. We can't just have some random node over here which isn't connected to the rest of the binary tree and then call this one cohesive binary tree. It's not, because every node has to be connected. We can put the node here where it's actually connected to another node, but we can't just have it floating randomly. All nodes have to be connected to each other. Now, there's another property of a node in a binary tree, which is called the height property, and it's mostly straightforward. First of all, we would measure a single node. We can say the height of a single node, like this one, is 1. We say that because there's just a single node, so we call it to be 1. The height of this is 1. It doesn't have any children. But for a node like this one, where it does have some children, we measure the height starting from this node, going down to the lowest descendant of the node. This is another keyword. Descendant basically means for some node, such as this one, a descendant of this node would basically be any child or any other node that comes beneath that one. So basically for the root node over here, every node in the tree is a descendant of that node. And it's also worth mentioning that another keyword used is ancestor, which is straightforward, just like descendant. It would mean that this node, any node that came basically in the parent chain of this node. So this is the parent node, this is sort of the grandparent, and basically any node going up that chain would be considered an ancestor of the original node. This node doesn't really have any ancestors because it doesn't have any parents, but it does have a bunch of descendants. But going back to what we were talking about, the height of this node is starting from this node going to its lowest descendant, which in this case it only has a single descendant. What's the length of the path? Or in other words, what's the number of nodes starting from here going to its lowest descendant? Well, we can count 2 nodes, so we say the height of this node is equal to 2. Can you tell me what would be the height of this node? Well, we could go down to the right. This forms a path of 2. That's the longest path we can form going on the right side. On the left side, we can form this path, which has 3 nodes in it. Clearly, 3 is bigger than 2, so we say the height of this node is equal to 3. I do want to mention that in some cases, people measure the height of a single node to be 0. So that would mean the height of this node is equal to 0. That would mean the height of this node, which we said was 2, would actually be measured to be 1. I don't prefer that way of calculating the height, but I just want to mention that sometimes in some textbooks and courses, people do that. So don't be too surprised if you see it, but the important thing here is whether we start at 0 or start at 1, the important thing is how you would actually calculate it. And I've illustrated to you that starting at the node, the height would basically be measured by finding the longest path going down. We have the opposite concept of height, which is depth. So what would be the depth of the root node? Well, it's measured as the path from here to the root node, and this is the root node, so we could say that the depth of this node is 1 based on how I like to calculate it, but some people would say that the depth is 0. What about for this node? What's the depth of this node? Well, what's the path from here up to the root node? Well, it contains 2 nodes, so I would say that the depth of this is 2, but some people, instead of counting the nodes, they would count the pointers connecting the nodes together, and in that case, you could call it to be 1. What's the depth of this node? Again, it's going to be the way I calculate it, it would be 2 because we have 2 nodes here. What about the depth of this? Well, it's going to be 1, 2, 3. So the depth of that node is 3 because that's the path from this node up to the root. So these are a lot of the key concepts that can come up when talking about binary trees. So I wanted to introduce you to some of the basics. So it wouldn't be complete if we didn't at least talk a little bit about the code. For now, I'm just going to cover the general structure of a tree node. It's pretty similar to a linked list node where we have a few properties. One is going to be the value. In this case, it's an integer, but it could be anything else. And also we're going to have a couple pointers, which could be different based on the language that you're using. But in general, they're going to point at a couple tree nodes, the left and right child. Initially, they could be set to null. And to add a child node, you would simply reassign this to the child tree node. And generally, when you create a tree node, you want to, at the very least, initialize whatever the value happens to be. So the value for this tree node, of course, is 2. The left pointer is pointing at this node. The right pointer is pointing at this node. So now we have a decent understanding of the basics